Okay, so this talk is about the problem of how you train a large language model if you don't have enough data. And it's based on a project at Hugging Face that was led by Nicholas Morninghoff. The talk today is in two parts. I'll first start by going through the problem of scaling laws. In the second part, I'll discuss the new components of this work that focus on this problem of scaling laws under data constraints. Let's begin by briefly introducing some key terminology. We're going to have three components in this work: the model size, measured in number of parameters, the training data, which is measured in number of tokens, and the training compute, which is measured in flops, floating point operations. These first two have a multiplicative relationship, so our total compute is a function of model size and training data. There's a constant factor alpha there, but you can mostly ignore it in this work. Applying this formula to known models, we can see that a model like BERT base starts out at about 109 million parameters and is trained on 250 billion tokens. This leads to about 1.6 times 10 to the 20th total flops. And at the time, it required about 64 TPUs over 4 days of training, but it's relatively small now. Jumping to GPT-3, we get to 175 billion parameters and about 300 billion tokens. And going to PaLM 1, we go all the way up to 540 billion parameters and about 780 billion tokens. We're starting to get much larger sizes, and at about this point in time, companies stop telling us exactly the numbers of their model. But what do we really need to know when making these decisions? If you're an executive and you want to decide how to train a model, there are two questions that might come to mind. The first we'll call return. This tells us how increasing one of these qualities will actually help in terms of our final loss. The second we call allocation, which is the question of how we should balance the different terms in this equation. Both of these questions are useful for determining the size and the amount of data to actually train. So we first consider the question of return. Results here mostly come from OpenAI in 2020. And they show us that the loss of these models is going to improve as a power law with each of these individual terms. Roughly, this means that if we plot things on a log-log graph, we will see a linear relationship in test loss. So this applies to model size, training data, or compute. For instance, in the graph for data size, we see that increasing from 10 to the 8th to 10 to the 9th tokens leads to a nearly 1 point decrease in loss. And these log-log graphs are really important. They've been the main force which has justified the kind of massive increase in the amount of compute applied to these problems. Just as important here is the question of allocation. When training a large language model, we need to decide a priori what the relationship will be between model parameters and the amount of training tokens. In 2022, a paper on compute optimal training, which is better known by its somewhat cute name, Chinchilla, showed a large set of empirical experiments that try to extrapolate out these values. Specifically, they calculate the best way to allocate a compute budget when deciding between model size, more parameters, and training data, i.e. more tokens. In this graph, they plot 4 large language models in terms of the number of parameters used and the number of tokens. The paper argues that previous models used too many parameters and not enough training tokens. In order to produce a compute optimal model, that is, a model that best uses its compute in order to decrease loss, they argue that we should use an equal relationship between the number of parameters and the number of tokens. They hypothesize that as compute budgets grow, this relationship will continue to produce the best model for a fixed amount of computational flops. Chinchilla will be the basis for the rest of the talk, and frankly, it's a paper anyone interested in this area should read in depth. In this work, they derived a relatively simple formula for estimating loss. This formula is a function of the model size and the training data. Here, n represents the number of parameters of the model, and d represents the number of tokens in the training data. We're going to try to write down a simple functional relationship, which will produce the prediction of the final loss. This formula is made up of 3 terms. The first term represents an approximation of kind of how good the model is to the true underlying generative process. The second term represents the fact that we only see a finite amount of data samples, and that if we had seen more, maybe the model would have done better. And the third term represents a lower bound. It's the best possible loss. In this case, it's the true entropy of language. The variables A, B, E, alpha, and beta represent empirical measurements that we fit on a large set of experiments. The results from the previous slide come from the fact that the empirical fit of this model yields terms alpha and beta that are approximately equal to each other. One of the implications of this formula is that we need a lot of data. If computers are getting better, people want to build better models, and these models will be increasingly data hungry. Researchers have predicted that the amount of needed tokens to feed these models is going to roughly run out in coming years, as represented by the graph on the left-hand side. This shows that we are already kind of getting close to the limits of the amount of data we have, and that more new tokens, represented by the dotted lines, are not being produced at a very fast rate. While this graph has large error bars, it's clear that in the next several years, we will exhaust supplies of available data. It's worth comparing this graph to actual data sources. If we are considering just high-quality language data, there are things available, like large amounts of academic papers at roughly 1 trillion tokens, and available books at roughly 1.6 trillion tokens. Other sources of high-quality data, like Wikipedia, provide more tokens, but are relatively small in size. If we allow ourselves to mix in code data, like GitHub, this provides us with about 14 trillion more tokens, which is a significant amount and could change some of these projections. However, things get much more dire when we consider specific languages. For example, if we are training a language model for Finnish, a language of 6 million speakers, there are only around 38 billion tokens available. This amount of data is already exhausted by current large language model needs. Starting from this motivation, we consider the question of data-constrained scaling. Our goal will be to reconsider the questions of return and allocation in a world where data is inherently constrained. In GPT-3, they say that data is sampled without replacement during training. And while they do repeat some sources like Wikipedia, generally they avoid this when possible. In the Palm paper, they note that they train all three models on exactly one epoch of the data, and that they choose the mixing proportions to avoid repeating data in any of the subcomponents. Generally, we find that the best practices for training large language models avoid repeating data. And so part of the question we are looking to answer is, why is this bad? Our approach will be empirical. For this project, we had access to a large supercomputer cluster and were able to run about 300 experiments utilizing moderately sized large modules. Throughout, we will consider three models, one using 2.8 billion parameters, one using 4.2 billion parameters, and one using 8.7 billion parameters. For each of these, we also have access to a compute optimal amount of unique data tokens. All models were trained with GPT-2 style transformers using hyperparameters from the Chinchilla paper. We utilized two web corpora, C4 and Oscar. In order to test the effect of repeating data for each of these models, we divided the data up into smaller bins. We trained the model 8 times, each of these with a different number of repeated data. To make things simpler, we use the term epoch. When we mean one epoch, it is one run over the entire data. But when we use the term 2 epochs, we mean that we repeat the data twice. This effectively means using half the amount of unique data. When we train the model with one epoch fully on unique data, we see the following standard loss curve. This loss curve is repeated for each of the 3 model sizes. We then move to 2 epochs. We see here that the loss curve is very similar, with only a slight difference at the end of training. This pattern continues when we move to 4 epochs. Here we are using only 25% of the original data, but we are achieving nearly the same loss. However, with more epochs, performance gets significantly worse. At 14 epochs, there's a major divergence in loss. And when we repeat the data up to 44 times, things have gone totally wrong. We run these same experiments using a different dataset known as OSCAR. OSCAR uses a similar domain of data, but is significantly more noisy than C4. From a high level, though, the main results hold here as well. Relatively little loss in return after 4 epochs, but things start to decay at around 10 epochs and get quite worse towards the end. These experiments show that the value of data clearly decreases with more repeats. And because of the large drop-off in loss with too many repeats, we hypothesized that repeating data could be modeled with some form of exponential decay. Each time we use a data point, it loses some fraction delta of its original value to the system. Intuitively, if it's helpful, you could think of this like radioactive decay, where each usage of the data represents some half-life of its original value. As the data is used more and more, its value to the system decays. Since using the data costs us flops, its underlying value becomes almost nothing over time. Formally, we model this by introducing a term d prime, which represents the value of repeated data. If our system starts with u unique tokens and repeating the data rd times, we compute the final value d prime using an exponential decay formula. Delta represents the value of the decay itself. If delta is equal to 1, then repeating the data is worth nothing. We might as well only use the unique tokens once. If delta equals 0, then we could repeat the data forever, and really there's no problem at all. If delta has a value of 0.5, then each repeated use of the data is only 50% as valuable, and the value of repeated training goes down quickly. For mathematical simplicity, we write this as a compounding term. Instead of directly modeling delta, we use a term r star d. This quantity represents the number of epochs we can reasonably run before experiencing a sharp diminishing return. If its value was 0, then repeated data would be worth nothing, and we should really stop after 1 epoch. But if the value was infinity, then we could go on forever reusing the same data. In order to fit this term, we need to set up our data in a slightly different form. Note that this is exactly the same experimental data we've seen before, but we'll show it in a form that makes it easier to understand the formula above. Here, when we say 100%, we mean a final data point trained on a 1 epoch model, whereas 25% represents the 4 epoch model, repeating the data. Remember that each dot here utilizes exactly the same amount of the underlying compute. In this graph, the dotted line here represents delta 1. That is the expected loss if there had been no decay. The dashed line represents the expected loss for delta 0. That is, repeated data yields no value. The yellow line represents the prediction that will be made by our mathematical model, and that's made by fitting under exponential decay. We ran 3 versions of this experiment, each starting with a larger model, as well as a proportionate larger amount of unique tokens. In all 3 cases, we see a similar relationship between the decay of repeated data and the final loss. Now we can also look at these projections in a theoretical sense. In this graph on the right-hand side, the x-axis represents the total number of training tokens used. Each point on this graph represents the number of epochs needed to reach that amount of tokens. The dotted line represents the expected test loss, assuming we had infinite number of unique tokens. Each point on the graph represents the expected performance of a model under this amount of repeated tokens. For each of these lines, the number of unique tokens is held constant. We can see that after 4 epochs, the expected repeated performance is quite similar to that of having fully unique tokens. But at 64 epochs, the prediction significantly diverges from the underlying dotted line. It starts costing us a lot more to use the same data. We see similar predictions again with the larger models. There is still benefit from repeated tokens, but the payoff for this return decreases over repeats. Next, let's return to the mathematical model. The predicted lines come from our variant on the chinchilla formula, taking into account the data constraints. We note that the formula is a function of the number of parameters and the number of data points. But we've seen that the way we're handling data points is to substitute the unique tokens d with a new variable d prime that takes into account the exponential decay of repeated tokens. To make the formula work, we also substitute in a value n prime that takes into account the fact that parameters are trained on less valuable tokens over time. Here we are making the assumption that over-parameterizing a model, but training it on repeated data, will learn less valuable features. Here, r star n represents the analogous quantity that corresponds to r star d for data. So this takes into account the number of epochs before the model stops really learning anything new. As in the chinchilla paper, we fit these new parameters, r star d and r star n, on a large set of over 200 empirical runs. The model returns us two values, one that says r star d is about 15.4, and the other is that r star n is about 5.3. Recall these are roughly the number of epochs before these two terms start to fully decay. Utilizing this formula, we can return to the question of allocation, how to decide how many tokens versus how many parameters we should use. If, for instance, you are training a language model and you have $50 million, you have to make a hard decision about how to allocate compute between model size and training data. But this question becomes even harder if you know you only have a limited amount of training data. Do you decide to train a larger model, or do you repeat your tokens more often? We can examine this question both empirically and utilizing our formula. If we look at the empirical experiments, we can draw a contour curve that shows the loss of various models trained with different numbers of parameters and for different numbers of epochs. If we look at this graph, the black star represents the chinchilla optimal model trained with 7 million parameters for one epoch on fully unique data. Each of the other points represents a different model trained with the same number of unique tokens, but for a different number of epochs and different number of parameters. The color of each data point represents its final loss. If we draw a contour plot around these points, we will see that we get an elbow-shaped curve, slightly below the chinchilla line. The points below the contour curve make sense. If we are willing to use more compute, we can decrease loss by either increasing parameters or increasing more repeats. The points above the curve are a little bit weird, as we start to get worse by adding more repeats or more parameters. Generally, for these data points, we use the same hyperparameters, and so things start to get significantly worse when we go out of that regime. In general, we exclude the points where we get bad results or overfitting, and so these don't factor into the analytical formula. We plot the predicted formula on the right-hand side of the graph, where we see the ideal contours that come out of the underlying equation. Here we see that the model continues to improve over a point, but that the improvement of the compute optimal model goes slightly below the chinchilla line. This is slightly counterintuitive. It implies that in a data-constrained regime, the allocation should go towards repeating more often as opposed to adding more parameters, as these parameters saturate more quickly in this data-constrained environment. We note that this is also implied by the R-star values. Given these theoretical predictions, we can also test them out in practice. In this curve, we trained two language models, They're trained with exactly the same number of flops and exactly the same number of unique tokens. The yellow star is trained to match the chinchilla formula. It represents repeating this token data to reach 178 billion tokens and 8.6 billion parameters. The red star represents the point predicted by our data-constrained version of the formula. This repeats the tokens to get 242 billion tokens and trains a smaller 6.3 billion parameter model. Given the same amount of compute, our approach achieves a better loss. Now, I want to be careful to explain this graph. In a world where we have infinite amounts of unique data, it is better to use the compute optimal formula. This only applies in a world where we need to repeat the data and it decays over repeated use. Another consequence of this formula is it allows us to go back and study previously released models. In the paper Galactica out of Meta, they train a large language model with 120 billion parameters. In this paper, they did in fact train it with repeated tokens, and in fact they trained for 4.25 epochs. However, and it was over-parameterized. Our formulas predict, though, that they should have made it even more drastic change to the model. They should have trained for an even longer amount of epochs for a slightly smaller model. So far, we've looked primarily at settings where data is constrained. While the results show that repeating data is promising, these results are somewhat pessimistic. They show that repeating can help, but that it is inherently limited. In this section, we consider alternative approaches without strictly relying on more tokens. We consider three different settings. First, we consider the repeating regime, which we have seen so far. Second, we consider an alternative approach where we fill out the remaining data budget utilizing code. As we've seen earlier, there is a large supply of code available on GitHub in terms of number of tokens. Finally, we consider the fact that token counts are for very clean corpora, but perhaps we could just utilize less clean corpora in order to just get more raw tokens. For these experiments, we can no longer simply use loss as the comparative measure. This is because when training on code or unclean data, we are changing the underlying data distribution. Therefore, we instead look at average performance across 19 different NLP tasks. In this graph, we show the performance of our system with repeated data and compare it to different systems utilizing code or less cleaning. The main takeaway we see from these charts is that code is actually an extremely effective way to getting more effective tokens. We see that the code curve does generally nearly as well as simply using repeated data, and that in fact, at a 50% code budget, we basically achieve the same performance, which is something that many of the large companies already seem to be doing in practice. Natural language tasks often have logical reasoning. Many of these tasks look similar in spirit to what is seen in coding data. We additionally see results for filtering, but these results were somewhat mixed. We see that removing aspects of perplexity filtering can give us larger data scale, but that removing duplication is less effective. These phenomena seem to be sensitive to the underlying data sets, and we don't try to draw any more general conclusions. To summarize the takeaways from this talk, we first described the general problem of scaling and how it works in the absence of data constraints. We then looked at the use of data constraints and saw that we were able to get around them by repeating 4 to 8 times with diminishing returns. Using these experiments, we hypothesized that we could build a mathematical model that would help us extrapolate the role of scaling. We used this to judge both the returns and the allocation of scaling large language models under data constraints. Finally, acknowledging that issues of scale may not be solved by data alone, we looked at complementary approaches to improve models. We find that utilizing code in addition to natural language can improve on practical downstream tasks. One nice consequence of these experiments is that we think we have evidence that we can train large language models using repeated data. And in experiments after the release of this work, some of the researchers on this team were actually quite successful in training a large language model for Finnish. This model uses 8 steps of repeated data, and the results from this model do show that these approaches can be useful in practice in improving both the loss and accuracy of models. Thank you very much.